Hey, if you are new here, this is Chandan and you are watching the learning field. Okay, so in this video is based on the how to make short note, revise and recalling the concept for the CSIR NET. Okay, and this video is based on the short notes on complex analysis. So from this video you can get an idea that how to make short notes, revise, how to recalling the concept. Okay, so you can say that this is one video, the full complex analysis in one video. Okay, there may be some terms or some concept or result may be missing, but this is the overall idea. I can give you the overall idea how to make short notes and so on. Okay, so let's start with complex analysis, revise and recalling. Okay, so if you like the content, then give a like to this video, share with your friends and subscribe the channel. Okay, so let's start the complex limit point. First start with limit of complex analysis. Okay, limit of complex valued function. Okay, so let we say fz has the limit at L at z equal to z0 if for given epsilon greater than 0 there is delta greater than 0 such that fz minus L is less than epsilon whenever z minus z0 is less than delta. Okay, so I make these short notes for myself some months ago, but I think that I'll share with you so that this maybe helps you a little bit. Okay, so now we comes to continuity. Okay, so what is the continuity? The complex valued function fz is said to be continuous if limit z tends to z0 fz equal to fz0, where fz equal to u plus iota b is continuous at z0 equal to x0 plus iota y0, and u and b are the continuous at x0 y0. If fz is continuous on C, then fz bar, fz whole bar, real z, imaginary z, sin fz, exponential z, exponential etc. are all continuous on the C. Okay, next we comes to the differentiability. Okay, so differentiability here, the differentiability is the complex valued function fz is said to be differentiable at z equal to z0 if limit z tends to z0 fz minus fz0 by z minus z0 exists, then we call the different function is differentiable. Now here is an important important note is that differentiability implies continuity but not conversely. This is also true for real analysis and this is also true for complex analysis also. So necessary condition for CR equation. Okay, so let fz equal to u plus iota b, then CR equation is ux equal to vy and uy equal to minus of vx. Okay, note here is an important note. The one is fz is differentiable at z0 implies f satisfies the CR equation at z0, and f is not satisfied CR equation at z0, then f is not differentiable at z0. Okay, so differentiable implies satisfies CR equation but not conversely. There is a result also. If it is satisfy CR, for satisfy CR equation and ux, vx, uy, vy are all exists and continuous, then this implies this is differentiable and analytic also. Okay, so next we comes to the simplest form of CR equation. Okay, so the simplest form of CR equation, this is also called the complex form of CR equation. Okay, complex form of CR equation. So let fz be a complex valued function, then del f del z bar equal to 0 at z0, then this implies CR equation satisfy at z0. If del f del z bar not equal to 0 at z equal to z0, f is not differentiable at z0. Therefore this we can say that to check the differentiability of a function, whether it is differentiable or not, first we check whether del f del z bar equal to 0 at that point or not. If del f del z bar equal to 0 at that point, then we can see that this is differentiable or satisfied CR equation, satisfied CR equation. Okay, and for to check non-differentiability of a function, if del f del z bar not equal to 0 at that point, then we clearly say that f is not differentiable. Okay, so this implies f is not satisfied the CR equation at z equal to z0. For example, if we take fz equal to z bar, then del f del z bar equal to 1, which is not equal to 0, that means f is nowhere differentiable. Okay, so this is an important term, f is nowhere differentiable. Okay, then the sufficient condition for the differentiability. Okay, so let fz equal to u plus iota b be the complex valued function defined on the neighborhood n of z equal to z0 such that ux, vx, uy, vy there exists in the neighborhood at continuous and at z0, then and satisfied CR equation, then f is differentiable at z0. Okay, the result I just say above. Okay, so there, for example, fz equal to x square plus iota y square, it satisfies the above conditions and CR equation satisfies only at y equal to x, so it is differentiable only at the line. See, I here write only the important terms and just one or two short example for understanding. Okay, so you can make the short notes this way. Okay, and also if you comment, also comment me if you like this content or not. Okay, and whether there is any mistake of mine. Okay, so important on analytic or holomorphic function. Number one is the important concept. Okay, so fz is analytic, this implies it is differentiable at uncountable point. Okay, and even or leaf, this means even or leaf, and fz is differentiable at countable point, this implies nowhere analytic. These results are very important. For example, let fz equal to mod z square, this is equal to z bar, is differentiable only at 0, that means it is nowhere analytic. Okay, so note, analytic in complex plane C implies entire function. Okay, this is also a note, and there are important result also. The result, let fz be a non-constant analytic function, then fz bar and fz whole bar never analytic. Okay, number two is if fz bar and fz whole bar are analytic, then fz must be constant. Okay, so this is an important result. So some important questions on constant function. Okay, let fz equal to u plus iota v be an entire function, if u equal to 0, complex value, v equal to 0, real value, u 0 means complex value only v present and v 0 means only the real part present, then u equal to constant and v equal to constant. And if mod f equal to entire function, image of f lies on straight line, all the above cases f is a must be a constant function. Therefore, to show or to check the options if f is constant regarding any questions, okay, so you must check these above conditions. If you see any of the conditions present in the question, then you can obviously say that or directly say that the function f is constant or f must be constant. Okay, so now it comes to what an important definition, which is harmonic function. Okay, that f equal to u plus iota b is said to be harmonic if del f del 2f del x2 plus del 2f del y, this is equal to 0. This is also you can say Laplace's equation, and I discuss a questions in the partial differential equation section. The Laplace equation is there is given the options uxx plus uyy plus 0. This is, I think, this is the question, and the options are, this is elliptic, parabolic, harmonic, this type of options given. Three options from partial differential equation, and one option I think it is harmonic. Okay, so the Laplace equation is an harmonic function. Okay, you can remind this concept for partial differential equation section also. Okay, so where u is equal to uxy and v equal to vxy, u and v are harmonic conjugate of each other. No, this is wrong. I think this is not each other. The concept is v is harmonic conjugate of u. Okay, but not conversely. Okay, so u and v, and whenever u and v are harmonic conjugate to each other, for that case f must be constant. Okay, or you can say that when f is constant, then u and v are harmonic conjugate to each other. Okay, and one more concept is that u is harmonic conjugate of minus v. I think this was there was a result. v is harmonic conjugate of u, and u is harmonic conjugate of minus v, I think. Okay, you can check and comment me in the comment section below whether it is right or wrong. Okay, so note u and v are harmonic implies u plus iota v is harmonic and uv are harmonic conjugate. Okay, and number two is u or v is not harmonic, this implies u is not harmonic. This is an important result to check the holomorphic or analyticity. Okay, now if u and v are harmonic conjugate to each other, then f is constant. This is right. Okay, this is right. Now example, for example, fz equal to z square equal to, you can say this is x square minus y square plus 2 iota xy equal to u plus iota b, u equal to x square minus y square and v equal to 2 iota xy, so that uxx plus uyy equal to 0. For v also this is satisfies the conditions of harmonicity. Okay, now therefore f is a harmonic function. Therefore, okay, so this is the definition of harmonic function. Now there is an example note 2, you can say if f equal to u plus iota b, u equal to this 3x square y, then ux equal to 6xy equal to by and uy equal to 3x square equal to minus of bx, then f equal to u plus iota b is equal to 3x square y is analytic, implies u and v both are analytic. Okay, but uxx not equal to 0, that means u is not harmonic, that means u is not holomorphic, that is the converse part of this. Okay, that means analytic but not this, there are both analytic but this is not harmonic. Okay, so this is important example. And now to find the harmonic conjugate of a harmonic function, there are three methods, I think. So method 1, let u given. Okay, so step 1 is first find ux and vy. Second step is ux equal to vy and v equal to integration ux dy plus phi x, this is the constant of integration. Okay, since u is taken as a since y is, x is taken as a constant, therefore we can write the integrating constant as a function of x only. Okay, and number 3 is use uy equal to minus bx to find phi x and phi dash x. Okay, these are the method. For example, let u f equal to u plus iota b and u equal to x cube minus 3x square y plus y square, find v. Ux equal to this we can find, and v equal to this is the formula based, this is just example. So this is equal to 3x square y minus y cube. Okay, this is the example. Now the method 2 is to find, just a minute, to find fz equal to u plus iota b when u given. Okay, so the method is f dash z equal to ux plus iota bx, this is equal to ux minus bx means minus ux means minus vy. Okay, so we put this is ux equal to ux, so this is ux equal to minus of vy. Oh, just put the value, sorry, this is vx, and vx equal to minus of uy. Okay, so this implies fz equal to integration ux x0 minus iota uy into z0 dz plus c, and this is known as the famous Milne-Thomson method. Okay, Milne-Thomson method. Now for example, find the analytic function f equal to u plus iota b, where u equal to cos hyperbolic x and sin y. So ux equal to sin hyperbolic x sin y, uy, find the value of ux and uy, and find ux z0 equal to 0 and uy z0 equal to cos hyperbolic z. Therefore fz equal to, just put the values in the formula, above formula, and we get here minus iota sin hyperbolic z plus constant. Okay, so this is the example. Now there is another method, this is method 3. The method 3 says that this is known as total derivative method. Okay, so using CR ux equal to by and uy equal to minus of bx, the total derivative is dv equal to, you know that dv equal to bx dx and by dy. Now put bx equal to minus uy and dx and by equal to ux dy. This implies v equal to integration of this integration plus you can take any constant. Okay, so for example, if phi equal to x square minus y square with a stream function with, this is I think a problem from CSIR NET, example from, okay, CSIR NET, a stream function psi with psi equal to 0 at x equal to y equal to 0. Okay, so we first find the phi x and phi y. So phi x equal to 2x, and this means since this is stream function, this is satisfies the conditions of analyticity, that means this is and satisfies the conditions of CR equation or satisfies CR equation, so that we can calculate the value of phi x and in terms of psi and phi y in terms of psi x. Okay, so this this is equal to 2y. Now we just put d psi equal to del psi del x dx plus del psi del y dy and find the value of psi. Okay, so psi equal to here 2xy. Now we comes to an important topic which is singularity. Okay, So this is singularity. Now what is singularity? A complex valued function f is equal to u plus r is singular at z equal to z0 if f is not analytic at z0. But remind that f is not analytic at z0, but in any neighborhood of z0 there must be a point in which the function is analytic. Okay, if there is no analyticity, then there is no singularity. Okay, remind this. Okay, so f is nowhere analytic, this implies there exists a singular point of f. Okay, for example, fz equal to z bar, f is nowhere analytic. Okay, nowhere analytic, missing term, so nowhere analytic, but f has no singular point. Okay, now here is a important diagram. Okay, I make this for my okay, but now I will share with you. Okay, so this is singularity. So types of singularity, I write the types of singularity in a table form. Okay, so mainly singularity are two types. Okay, isolated and non-isolated. Okay, so what is isolated singularity? If f is analytic in some deleted neighborhood of z equal to z0. For example, if z equal to 1 by z at z equal to 0. Okay, this is isolated singularity. And now non-isolated singularity, a singularity which is not isolated, we generally say that this is not isolated singularity. For example, if z equal to log z at z equal to 0. Okay, so this is the non-isolated singularity. Now isolated singularity are mainly three types. Okay, one is removable singularity, and the second one is pole, and third one is essential singularity. Okay, so what is removable singularity? This one. So if limit z tends to z0 if z exists finitely, this is removable singularity. For example, if z equal to sin z by z when z not equal to 0 and equal to 0 when z equal to 0 at z equal to 0, we know that limit z tends to z0, limit z tends to z0 sin z by z, this is equal to 1. That means the limit exists finitely. That means this is a removable singularity. Okay, now the pole, second one is pole. If limit z tends to z0 f z equal to infinity, that means exists infinitely. For example, f z equal to 1 by z minus 2 at z equal to 2, that means the singularity at z equal to 2, which is a pole. The third one is if limit z tends to z0 f z does not exist. Okay, so this is the types which is known as essential singularity. Okay, for example, f z equal to exponential 1 by z at z equal to 0. See, 1 by z at z equal to 0, this is a pole, but when we apply exponential function over this, then this is not a pole. Okay, we can't say that this is a pole. Okay, so this is a type, this type of singularity is known as a essential singularity. Okay, now non-isolated singularity, there is one type non-isolated, mainly essential singularity. Okay, so limit this is an important tagline is limit point of poles, which is known as non-isolated essential singularity. For example, f z equal to 1 by cos 1 by z. So cos the singularities are when the denominator equal to 0. That means if we put cos 1 by z, this is equal to 0, then this implies 1 by z, this is equal to 2n plus 1 into pi by 2. Okay, so that means z equal to 2 by 2n plus 1 into pi. Okay, so this is the limit points of poles and tends to 0 as n tends to infinity. So this is the example of non-isolated essential singularity. Okay, here f be a complex valued function and z equal to z0 is the point of singularity of fz. Okay, complex valued function. Okay, so this is the important concept for singularity. Okay, total singularity in just one table. Okay, now some recalling there are. So first one is the finitely many singularities implies all are isolated singularity. Second one is non-isolated singularity implies there are infinitely many singular points, uncountable number of singular points. This implies non-isolated singularities. Non-isolated singularity in the is the limit point of isolated singularities or poles. Fifth is limit point of zeros are the essential singularities. Okay, so limit point of zeros are essential singularities, and one another concept is limit point of poles are here it is not given. I think there is it is also given in some result. Okay, so then we comes to open mapping theorem. Okay, so this is says that any non-constant entire function f from C to C maps open set to open set. Okay, so the important recallings are if image of an open set is not open under analytic function, then it is an constant function. Number 2 is, we know that sin z, cos z, exponential z, pz means polynomial of z etc. are the non-constant entire function. Okay, image open sets under these functions are open. Okay, so remind this is a very important result or recalling. Okay, now it comes to Liouville theorem. Okay, so the Liouville theorem is what? This is simply says a non-constant entire function is unbounded, or it can also be say that a plus b equal to c. A plus b means what? Bounded plus analytic implies constant. Okay, so the contrapositive with this, bounded plus analytic implies constant. So note that entire plus bounded implies constant. This one is okay. So recalling, important recalling is exponential z, sin z, cos z, exponential sin z, exponential cos z, pz are non-constant entire function. So they are unbounded. Okay, in a complex plane. But remind that sin z in real, that is in sin x is bounded, but sin z is not bounded. Okay, just the fields are changed and the properties are changed. How? See, okay, this is an interesting facts. Okay, so range of non-constant entire function is either C or C difference alpha. This is the Picard's theorem. Okay, I make some days ago so that these terms are missing. Okay, so range of non-constant entire function is either C or C difference alpha. That means it can omit only one point. When if for any case if it omits at least 2 points, then it must be the constant function. Okay, now extended Liouville theorem. Okay, this is an also important theorem. Let f be an entire function such that mod of fz less equal to a plus b mod z power k, where a b greater than 0 and k belongs to n union 0, then f is a polynomial of degree at most k. Okay, an important note is, let f be an entire function such that mod of fz less equal to a plus b z power mod z power p by k, then fz is a polynomial of degree at most box of p by k. Okay, so the important result, there are three important results. Every non-constant entire function has singularity at z equal to infinity. Okay, that means the function, that is the polynomial in z, has singularity at z equal to infinity only. Okay, so a non-constant entire function cannot have a removable singularity at z equal to infinity. Okay, and number 3 is the entire function has a pole of order m if and only f has a polynomial of degree m. Okay, now it comes to the Picard's theorem. Picard's theorem, a non-constant entire function can omit at most 1 point. Okay, that is an entire function whose range omit at most 2 or more points must be constant. Okay, so this is the statement of Picard's theorem. Important recallings are, let f equal to u plus r to b and f from c to c be an entire function such that u or b greater equal to or less equal to or greater than or less than equal to, then f is constant. That means here are 4 cases given. Okay, u greater equal to a, u greater equal to, sorry, u strictly greater than a, v greater equal to a, v greater than b or a any constant, and the equality is also greater or greater equal to less or less equal to, and less equal to also. Okay, u less equal to a, less than a, v greater than a, v greater equal to less equal to a. These all are included in this line. Okay, total 8 conditions given on first line. And number 2 is u less equal to or greater equal to or less than or greater than v, then m must be constant. Here also 4 conditions given. Okay, now mod z less equal to or greater equal to or less than or greater than equal to r, there are 5 conditions given. Okay, mod z greater equal to r, less equal to r, greater than r, less than r, equal to r. 5 conditions total included in this option, then m must be constant. And 4 is u square plus v square equal to k square, and u square by a square plus v square by b square equal to 1, au plus bb plus c is equal to, then in that case also m must be constant. Okay, now it comes to an important definition, which is menomorphic function. The menomorphic function is that if each singularity of a function in the domain D are poles, then f is menomorphic. Okay, that means if for any function the singularities are only the poles, then f is said to be the menomorphic function. Okay, now it comes to Cauchy-Integral Theorem from integration of complex analysis. Okay, now Cauchy-Integral Theorem. Okay, so let fz be an analytic function of z, and if f dash z is continuous at a point within and on a closed continuity, then f dash dz equal to fz dz equal to 0. For example, fz dz by z minus 5, c is mod z equal to 3. That means this is a circle with center as 0 and radius is 3. Hence z equal to 5 lies outside C. Why? Says this is a circle of radius 3 and 5 point lies outside the circle. Okay, so 1 by z minus 5 is analytic inside and on C. Therefore, by Cauchy-Integral Theorem, integration 1 by z minus 5 is equal to 0. Now it comes to the Cauchy-Integral formula. Okay, this is also an important result for integration. Okay, so if fz is an analytic function within a closed contour C and a is any point within C, then fa equal to, that is this is the point of singularity, 1 by twice by integration fz by dz by z minus a, and in general fn a, that is if the pole is of order n, then this is equal to n factorial by 2 pi I integration over this. Okay, z minus a power n plus 1. For example, let mod c equal to mod z equal to 2. That means the contour is a circle of radius 2 and center at 0. Then 1 by z minus 1 square, this is a pole at 1 of order 2. Okay, so this is equal to 1 by twice pi I f of this is, if this is n plus 1, then this is the n. That means if this is 2, then this is 2 minus 1 at 1. Since 1 is the point of singularity, this is equal to 2 pi I into 0. This is equal to 0. Okay, now Cauchy residue theorem. Okay, so what is Cauchy residue theorem? If fz is analytic in a closed curve C except at a finite number of singular points within C, then integration fz dz equal to 2 pi I into sum of the residues at the singular points within C. Okay, that is, if a1 a2 an are the points of singularities, then integration fz dz equal to 2 pi I into residue of f at a1, that is residue of f at a1, residue of f at a2, and since so on, and residue of f at an. Okay, so method of finding residues. These are the important points to find the residue. Okay, so the number 1 is, if z equal to z0 is removable singularity, then residue at z0 fz equal to 0. So for the case removable singularity, the residue is 0. Number 2 is, if fz has a simple pole at z equal to a, then residue of fz at a, this is equal to limit z tends to z0 z minus a into fa. Okay, number 3 is, if f is a pole of order n at z equal to a, then residue of f at a is equal to 1 by n minus 1 factorial limit z tends to a d dz n minus 1, that is n minus 1th order derivative of the function z minus a power n of fz and into fz. Okay, so number 4 is, if fz is rational function, that is fz equal to phi z by psi z, then the residue at z equal to z0 fz equal to phi z by psi dash phi z0 by psi dash z0. Okay, now residue at essential singularity. What is the theorem? To find the residue at essential singularity, the expand the series and collect the coefficient of 1 by z, which is the residue. Okay, for example, exponential 1 by z equal to 1 plus 1 by z, this is the series of exponential z, this, and residue at z0 of fz, this means coefficient of 1 by z, and coefficient of 1 by z means here 1. Okay, so this is the residue as essential singularity example. Okay, now residue this is also an important form. The residue at z equal to infinity of the function fz. So residue at z equal to infinity at the function fz is equal to minus residue of z equal to 0 1 by z square into f of 1 by z. This is an important formula. Okay, this is an important formula. Now, for example, let residue of z exponential 1 by z at z equal to infinity. Okay, so fz equal to z exponential 1 by z, f of 1 by z equal to this one, and residue of z equal to 0 of 1 by z square, f of 1 by z is equal to 1 by 2 factorial. That means the formula is a residue at z0 of order, since this is of order 2, that means f and since f of 1 by z square, f of 1 by z is equal to 1 by z cube exponential z, that means this is a pole of order 3 at z equal to 0. Okay, so that this is 1 by 2 factorial multiplied limit z tends to z0 differentiable 2 times z cube into exponential z by z cube. So this is equal to clearly half. Okay, so limit z tends to z infinity, fz equal to minus limit at residue of z equal to 0 at 1 by z square, f of 1 by z, this means 1 by 2. Okay, now zeros of a function, this is an important concept. So a complex function fz is said to have 0 at z equal to z0 of order m. Okay, if fz0 equal to f dash z0 equal to f double dash z0 equal to f m minus 1 at z0, this is equal to 0, but if m z0 is not equal to 0, if m equal to 1, then z equal to z0 is a simple 0. Okay, now important recalling is if fz has a 0 of order m, then 1 by f has a pole of order m. Okay, number 2 is if hz equal to fz by gz, if fz and gz has zeros of order m and n respectively, then one is m equal to n implies removable singularity, m greater than n implies zeros of order m minus n, c m less than n implies poles of order n minus m. Okay, this is an important result also according based on 0. Okay, now we comes to identity theorem or uniqueness theorem. Okay, so the identity theorem or uniqueness theorem says that let d from c, f from d to c be an analytic function on d, and S be the set of all zeros of f in d, and if limit point of S contained in d, then f is identically 0. Okay, so this is the uniqueness theorem. Recalling, if f is analytic in a domain d and fz equal to 0 at countably many points of d, if limit point of d lies in d, then f is identically 0. Okay, example, let d from f from d to c, and d equal to f z, d equal to z belongs to c such that mod z less than 1 and f of 1 by n equal to 0, here s equal to 1 by n, then the limit point of s, set of limit points of s, this is equal to s bar, s dash, this is equal to 0, which is belongs to d, then by the above theorem f is identically equal to 0. Okay, and the general concept, if f of z1 equal to gz1, f of z2 equal to gz2, okay, and so on, and the limit points of the zeros of points are z1, z2 and so and zn. Okay, so if the limit points of these are suppose z star, if z star belongs to a domain d, then these are identically equal. Okay, so f is equal to 0. Okay, so this is an important concept also regarding identity theorem. Okay, now Schwarz lemma. Okay, so Schwarz lemma says that let f from this is a region to region bar, delta to delta bar, be analytic having a 0 of order n at z equal to 0, then one is mod of fz less equal to mod z power n, and 2 is f n power 0, that is nth derivative of f at 0, this is less equal to n factorial for all z belongs to that domain. Or Schwarz peak lemma, what let f be an analytic function on delta and mod of fz less equal to 1 and f equal to b for some ab in this region, then f power n at 0, that is nth derivative of f at 0, this is less equal to 1 minus mod fa whole square by 1 minus mod a whole square. This is also an important result. Okay, now go to argument principle. Argument principle, the argument principle says that let fz be a non-zero analytic function in a domain d subset of c except finitely many poles, then 1 by twice pi integration f dash z by fz dz is equal to n minus p, where n is the total number of zeros of fz and p is the total number of poles of fz. Okay, continued with multiplicity. Now the next important concept is Roche's theorem. Roche's theorem says that let C be a simple closed curve in D such that what f and g are two analytic functions inside and onto C. Mod of fz greater or equal to mod of gz for all z belongs to C. Then f and f plus g have same number of zeros inside C with multiplicity. Okay. Recalling, in general, take fz. How to choose fz and gz. In general, take fz as the term containing numerically largest coefficient of the polynomial in z. Okay. This is the recalling. And example, for example, this and there is an example. The number of zeros with multiplicity of the function inside mod z equal to 1, then the polynomial number of zeros of that polynomial. Okay. Take fz equal to numerically largest, that means minus z power 4 numerically largest coefficient, and gz equal to the remaining polynomial mod fz equal to 1 and mod gz less equal to this in 1, that means mod of fz is strictly greater than gz. So by Roche's theorem, f and f plus g have same number of zeros. Since f has 4 zeros, since this is a polynomial of power 4, so the given polynomial have 4 zeros. Okay, so this is the Roche's theorem. Now maximum modulus theorem, this is also another important concept, maximum modulus theorem. This is says that if fz is analytic and in a bounded domain D, then mod f does not attain its maximum value in D unless it is a constant. Okay. And minimum modulus theorem, if fz is analytic in a bounded domain D such that mod of fz not equal to 0 for all z belongs to D, then mod f does not contains its minimum value in D unless it is a constant. That means the maximum modulus theorem and minimum modulus theorem says that for any region the maximum value of a function cannot occur inside this region. Okay, this must contains the on the boundary of the region, and if the maximum value or minimum value occurs in the given region inside the region, then the function must be constant. Okay, and for minimum modulus theorem there is an extra condition which is mod of fz is non-zero. Okay, so for example, fz equal to z, D equal to z belongs to C, mod z less than 1. So mod of fz equal to mod z greater equal to 0. Minimum modulus theorem does not work at z equal to 0. Okay. Now the next important concept is radius of convergence. Okay. So the radius of convergence of a power series summation n z minus a power n is the distance between the point of expansion and nearest singularity. Okay, this is an very important question. Distance between the point of expansion and nearest singularity z0 of fz. That is, if n summation n z minus a power n is the power series representation of fz, then r equal to distance between a and z0, where z0 is the nearest singularity of fz from a belongs to C. Okay, the radius of convergence fz equal to this 1 by z minus 2 z minus 1 about z equal to 1. This is a problem from CSIR NET. Okay, so the singularities are z equal to 2 and 3 and the point of expansion is z equal to 1. Okay, so the nearest singularity from 1 is 2. So the radius of convergence is mod of 1 minus 2 is equal to 2 1. Okay, so result, if fz is entire function, then then there is no singularity. Okay, so the radius of the Taylor series is fz equal to infinity. Okay, the second result is if the power series a n z power n is convergent at z equal to z0, then it is absolutely in the disk, that is convergence absolutely in z minus z, that is z less than z0. If summation a n z power n is divergent at z equal to 0, then it is divergent for any z greater than z0. Minus r is the radius interval of convergence. If the power series n z power n has radius of convergence r, then the ROC of pz into an summation z power n is also r. Pz is a polynomial of degree d. To find the radius of convergence of the series 1 by r equal to limit n tends to infinity, this is the ratio test and this is the root test. Okay, if exist. Okay, so recall on Lorentz series. Lorentz series is a very important concept. So if fz has isolated singularity at z equal to z0, then fz has Lorentz series expansion. Okay, 2 is if fz has removable singularity at z equal to z0, if and only principal part bn equal to 0. So if fz has essential singularity at z equal to z0, then Lorentz series expansion of fz at z equal to z0 have infinitely many terms. Number 4 is the Lorentz series expansion of fz around z equal to 0 has infinitely many positive and negative powers of z, infinitely many terms. For example, exponential 1 by z equal to this series, principal part is infinite, then it has the essential singularity at z equal to 0. Remind that the Lorentz series has two parts, one is principal part and other one is analytic part. Okay, analytic part is this summation n equal to, I think it's 0 to infinity n x minus z minus z0 power n. This is, I think, remain the analytic part, and from, I think, z equal to minus n equal to minus infinity to 1 minus 1, I think a minus n z minus z0 power minus n. So I think this is the principal part. Okay, now it comes to the bilinear transformation or Mobius transformation. A map is of the form az plus b by cz plus d, ad minus bc non-zero for non-constant is a bilinear transformation. Recall a bilinear maps circle or straight line onto circle or straight line. Okay, bilinear transformation is 1 1 and on 2. Composition of bilinear transformation is also a bilinear transformation. There are some another concept also. Okay, so the important formulas for bilinear transformation is again in the tabular form. Okay, so transformation, condition and image. Okay, so fz equal to az plus b by cz plus d, upper half to upper half. Okay, condition is ad minus bc greater than 0, and the image is, this is upper half maps upper half. Okay, this is the z plane and this is the w plane under the transformation fz. Okay, the next one is fz equal to az plus b by cz plus b upper half to lower half when the condition is ad minus bc less than 0. So this is the upper half, this is the lower half, and the transformation is this one and condition is this one. This is the z plane, this is the w plane. Just a minute. Now the next one is fz equal to exponential minus I pi by 2 into az plus b by cz plus b, condition ad minus bc greater than 0, upper half to right half plane. Okay, so exponential minus iota pi by 2 means what? This is, we think, remind that if we generally we measure the angle in anti-clockwise. Okay, so this is the theta angle, and see this upper half part goes to this side, that means this is rotate clockwise by pi by 2, that means there is a negative sign. Okay, so upper half to right half plane. Now see this one, see since this is the measure of the angle in the anti-clockwise side, so there is exponential pi by 2 az plus b by cz plus d and ad minus bc greater than 0. The angle is the region is this one. Okay, upper half to left half plane. The next one is fz equal to exponential iota theta z minus beta by z minus beta bar, image of beta greater than 0, then this goes to upper half to unit disk. Okay, so this is the image upper half to unit disk. Okay, the next one is fz equal to exponential iota theta z minus beta by z minus beta bar, imaginary part of beta is greater than 0. Okay, imaginary beta greater than 0, this goes what, right half to unit circle. Okay, oh sorry, I think this is the outside the disk. Okay, just check once. Okay, and comments me in the comment section. Okay, next one is exponential iota theta z minus beta by z minus beta bar, real beta greater than 0, then this goes to right half to unit disk. Okay, this is the image right half to unit disk. And the next one is fz equal to exponential iota theta z minus beta by z plus beta bar, real beta less than 0, goes to left half to unit disk. This is the image, this is the z plane and this is the w plane. And next one is fz equal to exponential iota theta equal to into z minus z0 by 1 minus z0 bar into z, unit disk to unit disk, where the condition is mod of z0 less than 1. This is the image, this is z plane and this is w plane, unit disk to unit disk. Okay, so this is the content and this is the short notes of all complex analysis. Okay, there may be some result or concept may be missing. Okay, so I just I just make this presentation for myself some months ago. Okay, and I think that I'll share with you so that this can helps you a little bit. Okay, so if you like the content, then please give a like to this video, share with your friends and subscribe the channel. Okay, so मिलते हैं next video में. Thank you.